So, we will continue our calculation. So, here for this condition when low field and high temperature. So, we have derived the expression for the susceptibility, and this have the form of C by T, that is the Curie law, and C is the Curie constant. So, now actually for so I can so this whatever condition we have taken, this low field and high temperature. So, for classical theory, whatever result we got, this from here also, from quantum theory also we got for similar result, only slight difference of p effective, that is effective number of Bohr magneton. So, now if so, this is the original expression where we have not considered any condition. So, if you without considering any condition, if you in general if you proceed and you do calculation, so one can show, probably I will not calculate, but I can tell you few steps. So, I think I will just mention few steps, then it will be helpful for you. So, let us take this G, this term except mj equal to x, right, because this summation is over the mj. So, if I put x equal to Gj capital J, Gj mu v b by kbt, then this I can write, m equal to sum over, I think I will write slightly below, m equal to sum over minus j2 plus j, that is there, and this will give me, this mj will be there. So, I can take out this, gj mu v from here, gj mu v, and then put sum over minus j2 plus j mj e to the power mj x, right, divide by this one, sum over minus j2 plus j, this will give me e to the power mj x, right. Now, here if you just write the series, so minus j2 plus j, if you vary, what you will get, that you can just, I think it is yeah, it is not difficult one to write, but here one approach would be useful, that is this I can write, I think n, I am missing one n, yes, I am missing one n, there should be one n, and this I can write n Gj mu v, n Gj mu v, and here you see, if I take log of this and then differentiate it with respect to x, d by dx, okay, d by dx log of this, okay. So, log of this differentiate, so 1 by this, now log function that is taken here, then differentiation of this one. So, this will give me e to the power mj x, and this part differentiate with respect to s, it will give me mj. Okay. So, this can be written as ln differentiation of ln of this term minus j2 plus j minus j2 plus j e to the power mj x, right, mj x. So now you have to proceed, just explicitly write them, So, this ln I can write this one e to the power jx plus e to the power j minus 1 x, right. So, this way I can expand this series, we can expand that series and then do the differentiation. So, you have to just go ahead, and then what I will get, m equal to yes, m equal to n Gj. So, I will not calculate full, it will take time, but you can do the few steps. So, from here to here you can come n Gj mu v, that is your home task, it is not difficult one, I am telling the few steps. So, just fill up the gap. So, maybe after differentiation he will get this type of expression 2j plus 1, just let me, okay, 2j plus 1 by 2j cot hyperbolic, better I should write here, it will take, so n Gj mu v, So, if you do this, so you will get basically 2j plus 1 by 2j, okay. Then I will get cot hyperbolic 2j plus 1 by, I have to cot hyperbolic 2j plus 1 by 2j, then minus 1 by 2 j cot hyperbolic cot 1 by 2 j. Okay. So, this just j is yeah. So, here yes, now this either x should be there. So, that x here x I am writing alpha, So, this alpha equal to x by j. Okay. In between you have to put alpha equal to x equal to alpha j, So, then this place x was there, so x was there, right. So, that will come as a alpha. So, here this alpha term will come, yes, alpha. So, in place of x alpha term will come. Okay. So, this ultimately I will get, and without any approximation this will be the result. Please try yourself. I think you have to proceed. So, only when you are from here, when you are proceeding to get, so just you have to expand this series, do the series summation, okay, standard summation, you will find out, okay, and then in between you have to multiply with by e to the power x by 2, you have to multiply by e to the power x by 2 in both denominator, numerator. So, this into numerator and then this into denominator, okay, denominator. So, I think yes, e to the power x by 2. Okay. So, when you are doing step, so in one step just you have to take this one, okay, then proceed again, and then you will get this type of format, not except the j here, okay, except the j here. So, then if you take this alpha equal to x by j, and then in terms of alpha just x you have to replace by alpha j. So, then you will get this final format. Okay. So, this you have to consider. So, I think this way just it is just algebra, straightforward, only the some tricks one has to apply. Okay, then this. So, this is called basically n mu v n mu v g j, n mu v g j, and this is called. So, this b j is called Brillouin function, Brillouin function. This is called Brillouin function. Okay. So, yes. So, here's just yes mj. So, here when you will do step, so I am multiplying with by some this factor, right. So, here one j will come, So, that you have to include. So, in this final form here one j will come. So, here basically one j will come. Okay. So, this will be the final form without any approximation. This will be the m, this will be the m, and yes, and you see here this I can write in principle this Gj. What was the mu j? What was the mu j? I have just did mu j was Gj j mu v, right? Mu j equal to Gj j mu v, right? Gj j mu v. Okay. So, along the magnetic field mj equal to j, because mj value varies j2 minus j, j2 minus j, j minus 1, j minus 2, j minus 3 to minus j, right. So, when it is j value, mj equal to j value, that means it is aligned along the magnetic field. Okay. So, this Gj mj mu v, that is the component of this moment along the magnetic direction. So, now this mj is j, mj is j. So, that means this dipole moment is fully aligned along the magnetic direction. Okay. It is not component, it is fully aligned along the magnetic direction. Okay. So, as if this term is giving us this full alignment of this dipole moment along the magnetic direction, right. So, n number of them, right. So, all n number atoms having the magnetic moment, and they are fully aligned along the magnetic direction. So, that is nothing but the saturation magnetization. So, I can write this on saturation magnetization m equal to ms Brillouin function alpha. Okay. So, this m by ms. So, here that your b is there, here your b will be there, this b magnetic field, sorry, n mu b j. Okay. So, okay. So, I think this magnetic field inside of this function alpha, it contain this alpha. Okay. So, this ms equal to, so it is similar expression earlier from classical theory. What we got, this m by ms, it was Lenzman function, right. It was Lenzman function. Right. What is the Lenzman function? This cot hyperbolic alpha minus 1 by alpha, right. And this Brillouin function is this. Now, here just one thing you can see that if you take in this function here your if you take that condition, this term is less than this term, means x is less than, or L is alpha is very less than 1, Okay. So, from this Brillouin function, you can proceed, you can simplify it, and you can show that whatever before taking this one, whatever approximation we took, condition we took, So, we reach to the C by T Curie's law. So, from here also alpha is very less than 1 if you consider. So, you can go to the that Curie-Weiss law directly. Okay. And another aspect is here magnetic, here what is happening, this is the quantum theory, this is the quantum theory, and classical theory, this is the classical theory, right. Here Brillouin function and here Lenz's function, right. But one can show that here this what we considered, this dipole moment are free to rotate, and in this case what we have considered, dipole moment are not free to rotate. There is a constant, it can rotate only with 2j plus 1 value, 2j plus 1 value, this quantized value in space. Okay. So, that is the restriction. So, j equal to, it means it can rotate only in 5 directions, right. It can rotate only in 5 direction, 2j plus 1 is 5, j equal to 2, right. J equal to 1 only it has 3, it can have 3 rotation, okay, in space. So, that means if j value is smaller, it is more restricted, right. So, now if you take j value is infinity, j tends to infinity. So, then what will happen? J tends to infinity means mj value tends to infinity, 2j plus 1 is infinity towards infinity. So, then it is equivalent to the free rotation, right, as in case of classical theory we considered. So, when j value tends to infinity, then it is equivalent to the free rotation as we consider for classical. So, if you from this, in case of Brillouin function, if you considered j tends to infinity, then you can get this Lenz's function. From Brillouin function, it will convert to the Lenz's function. Okay. So, that you can check yourself if you take j tends to infinity. So, from here, so this Brillouin function will convert to the Lenz's function. Okay. So, Lenz's function this it varies Lenz's function is varies, not Lenz's function, this Brillouin function. Lenz's function I have shown you. So, Brillouin function as a function of alpha, it varies also, okay, like this. So, basically we are more interested about at the variation at the lower temperature, higher temperature and lower magnetic field instead of lower temperature, because alpha is by T, no, alpha is this by T, means this side is higher temperature, the other side is lower temperature, right. So, we are interested basically at the higher temperature. Why? Because at lower temperature and higher field, mostly you will get this system will go towards the saturation value. So, there is no much interest on this side at low temperature and high magnetic field. So, it goes towards the saturation value. Okay. In Brillouin function, this is varying like this, and in Lenz's function also we have seen it varies like this, right, it varies like this. But at higher temperature, low field approximation, we took the tangent at higher temperature, and this straight line actually we have shown that alpha, it is alpha by 3 under this approximation. So, this alpha by 3. So, this at higher temperature, this way, this function varies, or m, that function is nothing but m by ms. So, basically m magnetization varies with temperature at higher temperatures linearly. Okay. So, that in terms of chi, we have seen in terms of chi, we can see if I plot 1 by chi as a function of temperature. So, you will see it is a straight line. So, in paramagnetic case, this is for higher temperature. At lower temperature, we are not much interested, as I told, that it goes toward the saturation. So, that is why we are always considering the this higher temperature and lower field. So, it is straight line. Or if you just plot this chi and t, so it is a hyperbola kind of variation, because chi t equal to c, So, this basically this law chi equal to c by t, if you plot. So, this is the verification of paramagnetic material. If you measure the magnetization and then susceptibility and you plot as a function of temperature, then if curves follows like this, then we tell that is the paramagnetic material, and from this one can calculate the, in principle calculate the P effective, that is mu b, right. So, it is not just 2b, 3b, 5b, mu b, not b, 5 mu b. So, it is sometimes a fractional value, and this fractional value one can find out this. What is the average magnetic moment of each dipole of this, for this atom, for each atom. So, that one can find out from here, because from this slope one can get the c, or 1 by c, right, since it is 1 by chi, and c contain this all these things, right. I have deleted that one anyway, you know. So, from there we can calculate the effective number of Bohr magneton. So, and this is important because, as I told this, probably I will tell more about this. So, this about the quantum theory of this paramagnetism. So, let me tell something more interesting from this so, this there are very nice application of paramagnetic salt, you know. One application is cooling of, that is called basically cooling of this, of a system by adiabatic demagnetization, Okay, what is the meaning of that? Cooling by adiabatic demagnetization. So, if you take this paramagnetic salt, so by adiabatic demagnetization I can cool it, I can lower the temperatures. That is very important application of this paramagnetic material. You know this using liquid helium, we can go up to 4 Kelvin. I do not know whether you have seen or not, but we use in our lab this liquid helium to get temperature 4 Kelvin, and I think in many places this liquid nitrogen use, right, and that is 77 Kelvin. Okay. So, these are the discovery basically, and because of this liquid helium, because of this 4 Kelvin temperature one can reach. So, that discovery of superconductivity because of this, discovery of superconductivity because of the discovery of this liquid helium, which gives temperature of 4 Kelvin, right. Liquid nitrogen, it gives 77 Kelvin. So, it is easier to produce, and many labs it is produced and used for experimental purpose. But now question is how to go to the lower temperature from 4 Kelvin towards 0 Kelvin, how to go. That is a challenging, there are different way people try. So, liquid helium, this helium 4 basically. So, people use helium 3. So, some different mechanism to go lower than 4 Kelvin, but one efficient method is this cooling by the adiabatic demagnetization of paramagnetic salt. So, that I want to just discuss. So, what happens, you know the entropy is the measurement of the disorderness. For any system, if it is disordered, then its entropy is higher. If it is ordered, its entropy is lower. Okay. So, I have magnetic system, paramagnetic system. This paramagnetic system have the dipole moment. Now, if I apply magnetic field, I can align them along the magnetic field. So, that means before applying a magnetic field, they are disordered. Net magnetic moment was 0, net magnetization was 0. Now, if I apply magnetic field, then they are aligned, that means they are becoming ordered. So, their entropy, when I will apply magnetic field, their entropy will decrease, right. Or with respect to temperature, I have aligned system under say magnetic field. So, entropy is lower, right, and temperature is lower. Now, I am increasing the temperature, giving thermal energy to the system. So, it will try to disorder this dipole moment, right. So, increasing the temperature, it will be disorder more and more, its entropy will increase, right. So, entropy for this paramagnetic system in terms of dipole moment, orientation of dipole moments. So, this entropy, if I plot entropy versus this temperature, entropy versus temperature. So, this will vary like this, okay. This will vary like this. So, this lower temperature, entropy is lower, right, without applying any magnetic field, just as a function of temperature, the dipole moment of paramagnetic salt, this moment oriented. So, it is at lower temperature oriented, okay, along a particular direction, okay. And now, I am increasing temperature. So, it is disordered, entropy is increasing and entropy is becoming highest, right. Now, this for this curve for without applying magnetic field, Now, take a point here at temperature say Ta, at temperature Ta. Now, at this point, what is the entropy? So, this is the entropy value, right, this is the entropy value, fine. Now, entropy, this is the entropy, this is the very high value. So, system is disordered at this temperature, as this temperature. Now, if I apply magnetic field at this temperature, So, then what will happen? So, dipole moment, they will try to align along the magnetic field. So, they will go towards the ordered state. So, its entropy will decrease, right. So, its entropy will decrease, but at same temperature we are considering, say, entropy is decreased, it is taking this value. So, if I apply magnetic field, so my curve basically for this, so if you take this whole curve, so it will be like this. Okay. So, this will be for H equal to some value magnetic field B, H equal to B, say. Okay. So, this now this is the point where entropy is this, entropy is this, entropy is this, right. So, entropy decreases, earlier it was this. So, before applying magnetic field at this temperature, this was the entropy. Now, after applying magnetic field, it is in some extent it is ordered. So, its entropy changes, come down here, but at the same temperature. So, to keep the temperature same, we take the help of some reservoir, some conducting source. Okay. We keep the temperature fixed. So, this is the for isothermal case, right. And adiabatic case, this we do not allow thermal energy to go out from the system. So, its temperature will change. For isothermal case, we allow heat to go from the system to either to go out or to come in. So, that temperature will remain constant of the system. So, this change is isothermal change, right. So, just I applied magnetic field, system becomes ordered, keep the temperature at same temperature, then entropy will be this, it will decrease, okay, but temperature is same. Now, if I withdraw the magnetic field, now at this point, now at this temperature, now I have applied magnetic field. So, that is why it has come here. So, now I withdraw the magnetic field, then what will happen? I will withdraw the magnetic field and then, so it will go to this curve, because it is this curve for H equal to 0. Okay. So, what it will do? See, from here it came here after applying magnetic field. When I withdraw magnetic field, so from here it will go here, because in case of adiabatic, change of entropy 0, change of entropy 0 in case of adiabatic, dq equal to TdS. From there I can say anyway. So, in case of adiabatic, ds equal to 0. Okay. So, this now changing temperature, or just it will come back to its curve where H equal to 0. So, this is the point. Okay. So, this I can say this the temperature is Tb. Now, Tb is lower than Ta. Now, just I have applied magnetic field and then withdrawn. Now, the system's temperature is entropy is decreased and its temperature decrease, Then again from here I will apply magnetic field. So, it will be ordered. So, it will come here. So, again I will withdraw magnetic field, it will come back here. So, its temperature of the system will decrease. Again I will apply magnetic field here. So, it will come down here. So, this I will withdraw magnetic field, sorry, it will come here. I will withdraw magnetic field, so it will go back here. Okay. So, this just applying magnetic field, we do not need, temperature of the systems are decreasing. So, cooling. So, that is the very effective, technologically very important, and this is used for getting temperature to the up to I think towards 1 millikelvin, 1 millikelvin. Okay, from 4 Kelvin to 1 millikelvin. 1 millikelvin is 10 to the power minus 3 Kelvin. It's towards 0. It is towards 0. Okay. So, this is the application of this paramagnetic material, paramagnetic salt, and there are other things also, but I will stop here. I will discuss in next class. Thank you.